गुड इवनिंग बच्चों। आज का हमारा टॉपिक है इंटरनल एनर्जी ऑफ एन आइडियल गैस एंड इट्स चेंज इन इंटरनल एनर्जी दैट इज डेल्टा यू। सबसे पहले इंटरनल एनर्जी कैन बी रिटन एज काइनेटिक एनर्जी प्लस पोटेंशियल एनर्जी, बट इन केस ऑफ एन आइडियल गैस द intermolecular forces of attraction are assumed to be negligible. Therefore, we can say that potential energy is almost zero in case of ideal gas. Okay, so for ideal gas, its internal energy is nothing but its kinetic energy, and by the law of equipartition of energy, we can say that kinetic energy of each molecule of an ideal gas for each degree of freedom is half kT. Okay, so this is the, we can say, kinetic energy for one molecule of an ideal gas, where K is the Boltzmann constant, which is nothing but R upon N, where N is the Avogadro's number. Okay, now for one mole of gas, that is an ideal gas, I can say that kinetic energy is nothing but Avogadro's number N multiplied by half kT, which will be nothing but half RT. This is for each degree of freedom, that is for 1 degree of freedom. Okay, this is for each degree of freedom. Okay, and we know that kinetic energy is nothing but this internal energy. So we can say that internal energy U for 1 mole of an ideal gas will be equal to F into half RT, where F is the total number of degrees of freedom. Okay, this is for 1 mole. So we can say that for n moles of an ideal gas, U equal to N into F by 2 RT. Okay, where F is the number of degrees of freedom and N is the number of moles. अभी अगर हम इसको डिफरेंशिएट करें विद रेस्पेक्ट टू टेम्परेचर, देन वी विल गेट du इक्वल टू N F by 2 R dt, or we can say that delta U equal to N F by 2 R into delta T. This is a constant. Okay, and we also know that heat exchanged between system and surroundings at constant volume Q is given by N CV delta T. So if I equate these two equations, what I will get? We will get this CV is equal to F by 2 into R. Okay, because this N is common, here I can write N outside the brackets. So N into this into delta T, so CV equal to F by 2 R, where F is the number of degrees of freedom. Okay, now we can say that our formula will be CV equal to N, CV equal to F by 2 into R. Okay, where delta U equal to N CV delta T. Okay, so this is our formula. Now what is degrees of freedom for monoatomic gas? For monoatomic gas means when the ideal gas is monoatomic, the degrees of freedom is 3. All the 3 are translational degrees of freedom. For diatomic gas, for diatomic gases, this degree of freedom is 5. That is 3 translational plus 2 rotational. And for polyatomic gases, that is triatomic and polyatomic gases, its degrees of freedom is 6. That is 3 translational and 3 rotational. Examples of monoatomic gas may be your helium, neon, argon, and for diatomic it may be hydrogen, nitrogen, oxygen, etc. For triatomic or polyatomic it may be sulfur dioxide, sulfur trioxide, etc. Okay, so these are the formulas which we will use during our calculations for numericals asked in the past year exams. So we will take two examples to make it understand. So the formula is, I will write here delta U equal to NCV delta T, or I can write T2 minus T1, and other formula is CV equal to F by 2 into R. Okay, now let us take one question that was asked in 2019 main. It says that 5 moles of an ideal gas, 5 moles of an ideal gas at 100 Kelvin are allowed to undergo reversible compression. Okay, till the temperature becomes 200 Kelvin, means the final temperature T becomes 200 Kelvin, because when the gas will be compressed its temperature will increase. Okay, and the CV value is given to us as 28 joule per Kelvin, because this is joule per Kelvin. Okay, now what we will do, we have to find out delta U, and number 2 delta of PV. These two things we have to find out, and R is given as 8 joule per mole Kelvin. This is given to us, and there are 4 options given to us for these values, but we have to find out delta U and delta PV. So how we will do? We will apply the same formula, that is delta U equal to NCV T2 minus T1. Here N is 5 moles and CV is given to us, that is 28. This will be joule per mole Kelvin actually. Then T2 minus T1, that is 200 minus 100. Okay, so it will be 5 8 40, 140 into 100, that will be 14 kilojoule. We can say it is 14 kilojoule. So that is the value of delta U. And what about delta PV? Delta PV I can write as, we know for ideal gas PV equal to nRT, so I can write delta of nRT. N and R are constant, so nR into delta T, that is T2 minus T1, and by this we can calculate the value of delta PV, because it is 5 moles, it is given to us, so it N will be 5 moles into R is given to us as 8 into 200 minus 100, so it will be 40 into 100, that will be 4 kilojoule. So we have calculated the value of delta PV and delta U. One more example we will take, then we will wind up our session. This was asked in JEE 2005, and the question is 1 mole of a monoatomic gas, we know that for monoatomic gas the degrees of freedom is 3. Monoatomic ideal gas, it is 1 mole of monoatomic ideal gas. It expands adiabatically at initial temperature T. Initial temperature is given as T against a constant external pressure. External pressure is given as 1 atmosphere from 1 liter to 2 liter. Okay, and we have to find out the final temperature, and 4 options are given to us. Final temperature will be, and value of R is given as 0.082 liter atmosphere per mole Kelvin. Okay, and final temperature T will be, there are 4 options. A is T, B is T upon 2 to the power 5 by 3 minus 1. C option is T minus 2 upon 3 into 0.082, and the D option is T plus 2 upon 3 into 0.08. So these are the various options given to us. So how we will do? We know that this monoatomic ideal gas is expanding adiabatically against a constant external pressure. So whenever this gas expands against constant external pressure, the work done by the gas will be for irreversible expansion. So it will be minus of P external into V2 minus V1. So this is the work done. Because this is adiabatic process, so we can say that delta U equal to W, because for adiabatic Q is 0, there is no heat exchange. So delta U will be also equal to this. So I will put the value delta U equal to minus of P external, that is 1 atmosphere, into V2 minus V1, that is 2 minus 1, that is equal to minus 1. This will be liter atmosphere. Okay. Now we have found this delta U, and this we can equate to the value of delta U, that is NCV T2 minus T1. Here T2 is, say, T2 and initial temperature is T, and this we have found out as minus 1. Just we have found out the value by minus P external into V2 minus V1. It was minus 1 liter atmosphere. So N is 1 mole. Value of CV is for monoatomic gas. This is F by 2 into R, that is the CV value for monoatomic gas. Monoatomic, this degree of freedom is 3, so it will be 3 by 2 R. So we can write 3 by 2 R into T2 minus T equal to minus 1. Okay, so this we can say that T2 minus T will be equal to, this will be equal to minus 1 upon 3 by 2 R. So that will be equal to minus 2 by 3 R. Okay, and hence T2 will be equal to T minus 2 upon 3 R, and R is nothing but 0.082. So this is the T2 value, which is matching with our option number C. So C option is correct. Okay, this is how we can find out the values of delta U by NCV T2 minus T1, where CV will be equal to F by 2 into R, where F is the number of degrees of freedom which varies as per the atomicity of the gas. Degrees of freedom is 3 for monoatomic ideal gas, and it is equal to 5 for diatomic ideal gas, and it is equal to 6 for polyatomic ideal gases. With this, I wind up this session, and I wish all the best till the next session. Thank you.